So now that we've gone over some limiting reactant vocabulary and done things in a non-chemistry example, let's dive in and talk about how to do this with actual chemical substances. So procedure, gonna start out the same. Always start with a balanced equation. All right, next, this is the way that I do it. I calculate the mass of the product that the question is asking you for using the first reactant. Then do the exact same thing. Calculate the mass of the product using the second reactant and pick the smaller amount. A lot of times the book goes through and does, moles to moles. That's fine. Just pay attention to what the question is asking. So calculate the mass or the amount of product the question is asking you for. So here we go. This is an ammonia synthesis. It's a Haber reaction. So nitrogen and hydrogen makes two ammonias, or nitrogen trihydride, if you prefer that. So let's determine which one is the limiting reactant and how many moles of product we're going to form. So this is the same reaction. We're going to have three different calculations here. Okay, so if we have 3 moles of nitrogen, 5 of hydrogen. So let's start. 3 moles of nitrogen. Go to your equation. We know that 1 mole of nitrogen gives us 2 moles of ammonia. So 3 times 2 is 6 moles of ammonia. Our second choice, 5 moles hydrogen. Go to the equation. 3 moles hydrogen gives us 2 moles ammonia. 10 over 3. 3.33. 3.33. We'll shoot 2 moles of NH3. Okay, so this says determine the limiting reactant and how many moles of product. Okay, so make sure you answer the question. The limiting reactant in this case is hydrogen. That's what we run out of first. The amount of product that we make is the smaller one. So you pick the smaller one. This is the most product you can make. This is your limiting reactant. Let's try again. Let's use 8 moles of nitrogen, 4 of hydrogen. Moles of nitrogen. Go to the equation. Again, sometimes you'll have to go from grams to grams, so you might end up with a longer calculation. The principle is the same, just do it twice. And the equation says 1 mole of nitrogen gives us 2 moles of ammonia. So we can get 16 moles of ammonia. Or in this case, we can have 4 moles of hydrogen. It takes 3 moles of hydrogen to get 2 moles of ammonia. So 8/3, so that's what, 2.7 moles of NH3. Okay, so what's the limiting reactant? Once again, it is hydrogen. And then our theoretical yield, this would be our theoretical yield, if you want to do it that way, is how much product we can make. Because we can't make 16 because we're going to run out of hydrogen first. Last one, 8 moles nitrogen, 12 of hydrogen. We've already done 8 moles, so let's just skip that. We've already done that calculation. Save yourself some time. So 12 moles of hydrogen, and it takes 3 moles of hydrogen to get 2 moles of so here we're going to have 24, that's 8 moles of NH3. All right, so, well, once again, our limiting reactant here, hydrogen, and our theoretical yield is hydrogen. Let's try another example. All right, this is a methanol synthesis. So here we're going to have 3.00 moles of carbon monoxide, and we're going to start with 5 moles of hydrogen initially. So look, we're getting 3 questions. How many moles of methanol can be produced? What's the limiting reactant? How much methanol is formed? So we need to make sure we answer 3 questions. So we can put that, a lot of times I do the calculations and write the answers to these in a box somewhere at the end of the problem. So let's just dive right in. So 3.00 moles carbon monoxide. Go to the equation. 1 mole CO gives us 1 mole CH3OH. It's not a wasted step. So we can get 3 moles, or we can use 5 moles of hydrogen, and according to the equation, it's going to take 2 moles of hydrogen to give us 1 mole of methanol. All right, so that's going to give us 2.5 moles of methanol. All right, so we got some space over here, so let's start writing our answers. Okay, so how many moles of methanol can be produced? Pick the smaller one, this one. So we can say 2.50 moles methanol. What is the limiting reactant? The limiting reactant goes with the smaller amount. That would be hydrogen. And now it says what mass of methanol is formed. Oh, well, we need to figure that out. How do we get from moles to grams? Molar mass. You are correct. All right, so 2.50 moles methanol. Somewhere in one of these we've done recently, we probably calculated that, but I'm just going to calculate it again. 12.01 for carbon. There's 1 of them. There's 4 hydrogens. And there's 1 oxygen. So 1 mole methanol, see, sometimes I could start writing them upside down, equals 32.04 grams methanol. 80.1. So then there would be 80.1 grams methanol, and then I like to put a box around all the answers over there. Just makes it easy to find. Okay. Now let's do it again. This time we're going to have 4 moles of both, answering the same questions. So moles of carbon dioxide. And see, it says each reactant. In that case, you can go up here and you can say 4 and 4 if you want to write the quantities above there. Some people find that helpful. And we know it takes 1 mole carbon monoxide to give us 1 mole of methanol. So we can get 4 moles of methanol. Sig figs. Or we can have 4 moles of hydrogen, and it takes 2 moles of hydrogen to get 1 mole of methanol. So 4 divided by 2 is 2 moles methanol. Let's look at the question. Let's start answering them. How many moles of methanol? Pick the smaller one. 2 moles of methanol. Which one's the limiting reactant? the smaller one, the one we run out of first. So our limiting reactant is hydrogen. Grams of methanol, that will be our theoretical yield. So let's just take moles of methanol. And we used our molar mass up there. So 1 mole of methanol is still 32.04 grams. All right. 2 times 32.04, 64.08. So we get 3, so 64.1 grams. So our theoretical yield would be 64.1 grams methanol. Put a big box around it. All right, so here's another ammonia synthesis, different reaction. In this case, we are going to start with 86.3 grams of nitrogen monoxide, and we're going to start with 25.6 grams of hydrogen. And this just wants us to find the theoretical yield of ammonia in grams. So here we're going from grams to grams. So I am going to do my limiting reactant calculations going from grams to grams and pick the smaller one. Some of you are going to go just to moles of, or want to go just for moles of ammonia and then do one of these calculations. That's fine, I can follow it. That's not how I learned how to do it, so it's not my preferred way. But there's nothing wrong with that process. All right, so nitrogen monoxide weighs how much? Because we got to get to moles. 14.01 plus 16, so that'd be 30.01. 30.01 grams is 1 mole of nitrogen monoxide. Now we want to go with ammonia, and so it takes, go to the equation, 2 moles nitrogen monoxide gives us 2 moles of ammonia. And now the question is asking us for grams of ammonia. So since I know I'm going to have to do molar mass, I just do it anyway. 0.08 for hydrogen, 17.03. 1 mole NH3, 17.03 grams NH3. Some of you will stop right here and then do this calculation one time at the end. That's fine. 86.3 times 2 times 17.03 divided by 30.01 divided by 2. So there I got, we're going to round that up to 49.0. 0 grams of NH3. Now do the same thing again with your other reactant. 25.6 grams of H2, what's that, 2.02 grams of H2, 1 mole of H2, and now go to the equation. 5 moles of H2 gives us 2 moles of ammonia, not water, ammonia. And then we still have the same molar mass, 1 mole NH3, 17.03. So there we go from grams of one substance to grams through another, going through the balanced equation to get our mole-mole ratio. 25.6 times 2 times 17.03 divided by 2.02 divided by 5. These are not difficult problems. They just take time because you end up having to rewrite a lot of things. And so this here is 86.3 grams. So let's answer the question. The question says, find the theoretical yield of ammonia in grams. That would be the one we produce the least amount of. So that'd be this one. It only asks for one thing, so put a box around it. That's it. Let's try a couple more. Titanium metal, here's our equation. We're going to have 28.6 kilograms of carbon, and it's going to react with 88.2 kilograms titanium oxide. This time it's telling us how much we made, and it wants to know the limiting reactant, our theoretical yield, and our percent yield. So let's go ahead and start with what we're given first. So 28.6 kilograms of carbon. Now, what do you notice about this? We're in kilograms. That's right. Do we do molar mass in kilograms? No, we do not. So let's take 1 kilogram. Let's get to grams. Okay, so now that we're done with that, now we're with carbon. Periodic table says 12.01. 12.01 grams of carbon is 1 mole of carbon. So now we're in moles, and we're trying to figure out elemental titanium. So 1 mole of carbon gives us 1 mole of elemental titanium. And we know that 1 mole of titanium is, find it on the periodic table, 47.87 is what I'm going to use. 47.87 grams of titanium. What's the question asking us for? Kilograms of titanium. So here we need to go back the other way. 1,000 grams is 1 kilogram. All right. Now, yes, it is important to do these unit conversions. However, if you say, oh, there's 1,000 in the top and the bottom, you're correct. You can cancel them out if you want. Or you can plug them in. They're going to cancel out. So 28.6 times 47.87 divided by 12.01. All right, so that's going to give me 114. 14 kilograms of titanium. That's when we use carbon, but we also have another reactant. So let's see what happens when we use titanium oxide. All right, so we're in kilograms. We cannot operate in kilograms. We must go to grams. Now, titanium oxide weighs how much? Titanium, 47.87 plus 2 oxygens. So 79.87 grams of TiO2, 1 mole. That would be titanium 4 oxide. Okay, now titanium 4 oxide 1 mole gives us 1 mole of elemental titanium. And we know that 1 mole of titanium weighs 47.87. You already wrote it down once, and now we got to get to kilograms again. So 1,000 grams is 1 kilogram. And again, if you want to mark out your thousands, good. 88.2 times 47.87 divide by 79.87. 52.9 52.9 kilograms titanium. All right, so now we can start answering the questions. What is the limiting reactant? Limiting reactant is titanium oxide, titanium 4 oxide. What is our theoretical yield? The lowest amount, 52.9 kilograms of titanium. Make sure you are sticking with which product is correct. But the question says we only made 42.8 kilograms out of the possible 52.9 we made. So 42.8 kilograms over 52.9 kilograms times 100, because remember this is actual yield over theoretical yield. So 42.8 divided by 52.9. We'll use this theoretical yield in the lab a lot. So let's just say 80.9%. All right, so a lot of times I write all these together, but it works out. Okay, this is the last one. Nope, not. This is a really complicated one. But, so here, again, just read what the question is asking and you can figure it out. Iron 3 oxide is going to react with carbon monoxide. Here's the equation. Our reaction contains 22.55 grams there. So here, this says how much excess reactant remains. So first, we need to figure out what we're going to run out of first. So here, this is probably easier. Just pick a product because we're dealing with, because it wants to know what is our excess reactant. And there's no reason we need to go all the way to grams, so I'm going to stop here in moles. You can go to grams, it just adds some extra steps. So let's just pick iron because it's going to be easier to add a molar mass. So, all right, let's start with 22.55 grams Fe2O3. All right. Actually, let's do this. Let's say we have, let's see how much, since we can just compare these two products if we want to, or these two reactants. So Fe2O3 is iron 55.85. 2 times 55.85 plus 3 times 16. So 159.7 grams equals 1 mole. Okay. All right. Now, and we know that in the equation we use 1 mole Fe2O3 for 3 moles of carbon monoxide. So to react, so for all the iron, let's calculate how much carbon monoxide we need. Let's just start there. So 22.55 times 3 divided by 159.7. So this says for all the iron to react, we're going to need 0.424 moles of CO would be needed. Now, let's calculate how much carbon monoxide we have. We have 14.78 grams of carbon monoxide. Carbon monoxide weighs 12.01 plus 16, so 28.01. 28.01 grams of carbon monoxide, 1 mole carbon monoxide. 14.78 divided by that, 0.528 moles of CO. All right, so we have more than enough carbon monoxide to react with all this iron. So we're going to run out of iron first. So that means we're going to use up all of this carbon monoxide. So let's just subtract that. That's how many, we're going to say this is how much we have on hand. Now we're going to subtract 0.424 moles of our carbon monoxide that we actually use in the reaction. So that's a 4, that's a 0, that's a 1. Moles of carbon monoxide remaining. And now it wants to say how much in grams. So now let's go back the other way. So 0.104 moles carbon monoxide, 1 mole, 28.01 grams carbon monoxide. 0.104 times 28.01. So 2.91 grams carbon monoxide remains. That one's tricky. There's probably one like that on the homework. I may put one on the test like that, but that's very tricky. Now, determine the percent yield of the following reaction. That's what it wants us to find. If we are given 10.65 grams of hexane is going to react with excess oxygen to produce this much carbon dioxide. All right, so is this a limiting reactant calculation? No, because we have excess. It only gives us 1. So you can calculate the percent yield even without a limiting reactant. Let's balance this equation. Pause the video. You try to do it yourself. 6, 14, 7, 12, 19, 2, 12, 14. All right. Hopefully you got that balance correctly. Now, start with the amount that we're given of our reactant, hexane, C6H14. Now, let's go to moles. 12.01, 6, 14 times 1.008 for hydrogen. 86.17 grams C6H14, 1 mole C6H14. All right. Now, what is our second substance we're going to in the equation? Carbon dioxide, and it's in grams. Okay, so let's go with carbon dioxide. So how do we get from hexane to carbon dioxide? We go through the equation, you're correct. 2 moles C6H14 gives us 12 moles of CO2. Again, go back to the question, see if we're done. No, we want grams of CO2. 12.01 times plus 16 times 2. 44.01. 1 mole CO2, 44.01 grams of CO2. Okay, so this is our theoretical yield. So 10.65 times 12 times 44.01 divided by 86.17 divided by 2. So that means we can make 32.64 grams of CO2. Now the question asks us to find the percent yield, which equals our actual yield, 23.75 grams, theoretical yield, 32.64 grams times 100, 23.75. See, look, grams cancel out, divided by round times 100, 72.8, roundabout. Again, depending on how you round, you may get 72.7 and such. So those are the examples of how to do limiting reactant, theoretical yield, percent yield types of calculations.